All right. Just out of curiosity, could I just see by the raise of hands how many practicing architects are with us today? Okay. Nice. Thank you. All right. So, yeah, just want to thank the organizers for inviting me and showing interest in our study. And I think that despite being a very small field, it's very, very nice to see so many people. Yeah, my name is Zakaria, or simply just Zach. This is how most people just refer to me. Yeah, I'm the PhD student from Aalborg University, and my research interests include understanding architectural transitions through predictive bodily mechanisms. We conducted a study in Berlin with the Mobile Brain Body Imaging Lab of TU Berlin. It is entitled, as you can see, Architectural Cognition, the neurocorrelates of spatial affordances during transition in architectural settings. And I chose to do a more architectural biased presentation today, since I sort of saw it coming that there would be a lot of architects today. But if you have any questions on the brain processing, I will be here also for the next couple of days. So I want to just continue to give you the historical background of transitions. And this takes us back to Egypt, where we see some of the very first indications of some awareness of the bodily impact on a transition. We see, for instance, here that they have the division of spaces. And it seems also that as they keep on building, they seem to be even more aware excuse me, of the bodily impact of transitions. The Egyptian architecture was the source of the Greeks, and they seem to have noticed this impact. And they start to speculate on the origin of this impact of the transitions. And we see that some of the modern writings in architectural transitions all are inspired by Pythagoras, simply. Plato, for instance, in his Timaeus shows interest in natural relations. And here he even goes on and to mention the continued geometrical proportions. Vitruvius read a lot of Pythagoras as well. And he also sees a lot of shows a lot of interest in the geometrical proportions of space and those that are in relation to the well-shaped man. So here we see some of the early indications of geometrical proportions compared to the well-shaped man. Alberti also studied a lot both Plato and Pythagoras. And he created these very precise mediocrates that are very precise relations of body versus space. And he goes on to praise the importance of these proportions. Palladio even states directly that beauty will result from the form and correspondence of the whole with respect to the several parts with regard to each other, and of these again to the whole. And here's just a classic example to show how some of these natural relations are used by, for instance, Palladio in his architecture. We have here the Villa La Rotonda. I hope everyone knows this. It's in Vicenza, Italy. And here he simply created a grid and implemented some of the natural relations. But analyzing these mentioned writings and Egyptian architecture and the bodily impact of a transition, one might discover that the ancient numerology simply is insufficient to explain the bodily impact of a transition. And we state that maybe this is because there is a disembodied imperception of the transition itself. And also it disregards the movement, as in how do you move from one space to another. It neglects the continuity, and in the end becomes a discussion of what you might term absurd formalism. We think maybe that it's time to think about architectural experience as it appears to us, which is in action. Something sort of like the architectural promenade as it is introduced by Le Corbusier. We find it also in the end that in fact transitions are very rich and complex. So with this we find that cognitive neuroscience might be able to explain how these bodily impact of transitions might affect us. I'm talking specifically about the predictive processing in cognitive neuroscience. Put very briefly, the theory states that we are predictive across hierarchical levels. that is from sensory motor to higher cognitive functions, such as decision-making, intentions, and feelings. Most importantly, it also states that we are constantly making active inferences about the world, and that we perceive as we act, and we act as we perceive. And this would, just to give you like a small background on this, the early perceptual processes and the motor-related cortical potentials, also known as the MRCPs. So MRCPs are EEG components. I don't know how to explain this in a proper way so everyone can understand, but these are components that you can measure with the EEG, and that these are always showing up universally from anyone. And motor-related cortical potentials are those that are related to any movement. So, and you might ask, how is all this related then to transitions? And early perceptual processes, inactive inferences, can be explained as affordances that were first mentioned by Gibson. And this is a more recent definition by Andy Clark. And he goes on to say that affordances are the possibilities for use, intervention, and action which the physical world offers a given agent, and are determined by the fit between the agent's physical structure, capacities, and skills, and the action-related properties of the environment itself. And we think that this is a way more embodied approach to understanding how we actually move in space and how we transit from one space to another. And so with this knowledge, we construct that motor planning and motor execution are deeply related. And it seems that how we execute is informed by action and perception loop, as introduced with the active inference. We also find that in motor planning, we have affordances that are constantly processed but not necessarily executed. And this is usually expressed in some MRCP component, also known as slow cortical potentials. This is just one of them, the contingent negative variation, also known as the CNV component. And motor execution usually is expressed through some bodily trajectory, as we know it, as a form of behavior. And we think that this whole system is a dynamic embodied process that might be able to explain how transition, the impact of a transition really occurs. And from all this, we create some hypotheses. One of them is a temporal, on a temporal scale, that states that processes of perception and action potentials happen simultaneously. We also hypothesize that affordances can be explained as a function of early perceptual processes, and the willingness to act depend on affordances. And last but not least, the affordances can be explained as a function of anticipative MRCPs. I should just briefly state that the contingent negative variation is an anticipative ERP component. Yes. So they have been already investigated as something that is anticipative. So briefly about the experiment that we conducted. It is an S1, S2 paradigm. I will explain in a second what that is. It included an action-oriented goal. We had 240 trials with 20 participants. So our participants were situated in a VR space and were instructed to pass through some openings and touch the red coin, which would in turn give them some monetary reward. They would have to pass back and to answer some questionnaire. And these are the different doors. So this is a white door. The gray shape you see is the door. This is a wide door, this is a mid door, and this is a narrow door. The narrow door is impossible to pass. You can see here the dimensions. The narrow door is 0.2 meters. No one is that slim. Mid, wide are easily passable, for some, of course. So for the sake of the example, I will just show you down there as well, the timeline. Our participants were in a pitch black environment because we placed a black sphere around their head. And they would then, the sphere would pop, and this is known as the S1. This is the warning stimulus. Here the participant is able to see what do I have to pass. He then waits for 6 seconds and then gets either a green door or a red door. For the sake of the example, he gets a green door, he passes through, gets to his monetary reward, comes back, answers the questionnaire, and he restarts. In case of a no-go, he simply turns around, answers the questionnaire, and restarts. And the approach is a mobile brain body imaging approach, and this is one of my colleagues showing here that she is situated in a VR environment. She's equipped with a bag which holds a computer which is connected to the VR system. We attach batteries to keep it completely wireless, and we attach also ANT Neuro64 channel. And this is how they're all linked. We use Windows Mixed Reality, ANT Neurosport, and a Zotac computer. Everything is linked with the lab streaming layer for event markers. And just briefly for the results, we found that, for instance, in the reaction time, people move much slower when they have a narrow door, so they take more time. And this is an early indication that people are less willing to move when they know it is impossible to pass. I should also mention that out of 240 trials, they were all pseudo-randomized, the doors, and all had 1/3 each. And they knew very fast, the participants, that it's impossible to pass the narrow door, but they were always asked to try, which was very, very painful for them. For the S1, that is the warning stimulus, here's an example of some of the ERPs. I here show only the frontal-central channels, and we see a clear difference for the narrow door and the wide and mid door, grouped as passable and impossible to pass. As early as 200 milliseconds, which is usually thought of to be during perceptual processes. And to our surprise, we did not find any MRCPs between S1 and S2. So instead, we tried to think maybe this has to do, well, either the paradigm is not designed for being able to discover MRCPs between S1 and S2. So instead, we started to look at the post-imperative negative variation, that is, the negative variation after knowing whether I can go or I cannot go. And we see here that there is a clear, again, this is frontal-central channels. We see again here that no-go gives us absolutely no differences, while go gives us differences. I should state that the vertical line is the event of he knows whether he can go or not go. And we see significant differences in the go between 600 and 800 milliseconds. Just to give an overview of the statistical results, the S1 shows clear differences between 50 milliseconds to 250 milliseconds, and we see no differences for the no-go in the PIMF component, but only differences in the go, most expressed between 600 and 800 milliseconds. To conclude, perceptual processes and action potentials happen simultaneously. We find that to be somewhat true. Of course, you cannot just say that this is true, but there are definitely some clear indications that points towards that direction. We also found that affordances can be explained as a function of early perceptual processes. This means that when we see the differences in the P200, which was the early perceptual process, they correlate with the width of the doors. And we also see the willingness to act depend on the affordances. This is illustrated by the reaction time. However, we were not able to find that the anticipative MRCPs could be explained by affordances. This was really the most shocking thing, actually. Just to sum up, so we looked at the affordances at an early stage of perception, and the next step here will be to analyze the brain dynamics as one is moving towards the door. We find that the transitions, in fact, are very complex, consist of very complex bodily transitions, processes, and that we are clearly very predictive in our nature. And so we think that the narrative of architecture maybe is even more important than we thought of before. It is a fluent and embodied transition all the time. And so architecture can influence cognition. And since we are put in this session, I thought maybe it was really important to address some of the challenges that one might face when you try to measure architecture. So when can we move from virtual reality and reality, and when is the immersion sufficient and translatable? I think this is some of the good points that also Vikato touched upon. And for the equipment, there is definitely some technology and cost that should be considered. Static and dynamic environments, I see that I'm asking, are static experiments addressing architectural experiences? We see that there are huge differences between whether you have to act when you get a go and when you don't get a go, like a no-go. So this really puts into question whether you can actually conduct an architectural experiment without actually having to move. And in our experience, we find that linking the known brain functions to systematic architectural variations works really well for us. And this is because the well-studied cortical functions can give us a paradigm that we can sort of manipulate with architectural variation. And if there is any difference, we can somehow attribute the source of difference to architecture. We found that as functioning really well, but we are really, really open. We really want to address this question. We're really open to receive other ideas. Yes, thank you.
Any questions?
Thank you. Excellent work. I strongly encourage you to look up the work of Michael Benedict from the late 1970s. His work on isovis and isovis fields, the way information opens and closes as you move through environments. He's got a good way of measuring that, and there's been a lot of work done on how that affects people's actions and activities and emotive responses in the way environments open and close, particularly when measured as isovis fields. So it ties in very directly to your work.
Thank you. I like the isovist idea and the analysis of isovist, but I think it's good, but I think also it's kind of insufficient because in this experiment, in fact, we had half of the experiments, when they passed through the door, it was a double as high room versus the other. It was like either continuous room height or a higher room. And the next step also in of the analysis will be to see whether there are differences if you transit from a small space to a higher space. We just did not reach to this part yet. It takes time to analyze stuff. But the problem with the isovist is that it does not consider whether there is a different height space, and it only looks at the plan level. Although, other than that, you would have to sort of flip the isovist into some section.
You can have three-dimensional isovis, but yeah, most of the software and stuff you see is just a two-dimensional plain isovis.
Three-dimensional sounds really interesting. I will have to look into that. Thank you.
Any further questions? Yes?
Curious if you have the technology to take this experiment into the live world of architecture and not into a...
You mean not virtual reality, but real reality?
Into like walk them through a series of spaces and analyze.
Can I answer?
Yes.
Yeah. I think that's really, really a good question and suggestion as well. But the thing is that we have been discussing this quite early, and the problem is that you need 240 trials to get a stable ERP. How would you do that in real life? And the question is also that when you go, say for instance, you want to do a real life experiment, the sunlight changes, you have windows, it will change the light settings. And there's so many things changing all the time in the real life, and this is some of the variables that we cannot control, but I really would like to look into single trials, so it could be interesting.